Alright, so my name is Josh with Parfait. Today I'm going to be talking to you all about the lab that we did last week on the refrigeration cycle. So first I'm going to go over how it works a little bit. There's actually two fluids in a cycle going on simultaneously. You have the water and you have the refrigerant. You have a hot side and a cold side. So basically, refrigerant goes through a compressor into a condenser. It gets cooled by lukewarm water. It comes through a condenser, it goes to your expansion valve. Your expansion valve is kind of a unique piece because it actually controls how efficiently your system runs. It controls the refrigerant that goes to the evaporator. So basically, too much refrigerant, you're not going to run as efficiently as you should. Same thing with too little. So after that, the cold refrigerant goes into the evaporator where it comes into contact with the warm water. It cools the water, and then in this case, if you're trying to cool something, you tap into this cool water right here, and then you can go ahead and cool whatever you're looking for. So for the procedure, basically we just turn on the compressor, we turn it to 40%, and then we controlled how much water was going into the condenser or how much water was going into the evaporator to control our coefficient of performance. So these are some calculations that I did, and also some assumptions that we made. So basically the big assumption is that heat transfer between the water and the refrigerant was equal to one another because there was no entropy involved. I found an uncertainty. The uncertainty was basically just due to the resolution of the devices that we used to get the data, which was plus or minus 0.01. And in order to calculate how much energy was lost from the water or gained from the water from the refrigerant, we used the energy change equation up here, which is Cp delta T. Alright, so right here I have a picture of a TS diagram. Basically the green is the ideal cycle, the yellow is the real cycle. Pay close attention to how much area is to the right of this saturation curve. Basically, as we go forward, I created pH diagrams that you're going to see as the coefficient of performance goes up. This 2 point is going to be closer to this green curve. So I know this looks like a lot, but basically it's just the values that we started with on the condenser side for the water, and then we have a pH diagram here. So 3 is the water that went into the compressor. That's where our cycle kind of starts. 1, you're exiting the compressor. 2, you're exiting the condenser. And 3, you're exiting the expansion valve in this case. So this was when we had 0 liters per minute going through the evaporator. All right, so now I went ahead and this was our first case where we had 6 liters per minute going through the evaporator. So as you can see, our 4 moved over to the right a little bit right here. And because we're moving away from the saturation curve in the ideal, the 4 state would be right on it. You can see that as we go on, you'll be able to see that it changes the coefficient of performance. So right now our coefficient of performance, it's how much cooling you got out of it or the work that you put into it to make it, so obviously power the compressor and things like that, and that's going to be 2.046. Beta is your coefficient of performance. The reason why we use beta in this case is because in a refrigeration cycle, it's kind of hard to say this is the amount of work out, the workout that you got, and then over the work in, because you're actually mainly looking at how much heat loss you have or how much heat gain you have. So it's always going to be over 1 instead of in the efficiency case, it's under 1. So we're going to move on to the next one. We have 4.5 liters per minute. Now here, as you can see, our efficiency went up, and actually our state 4 moved over to the left some, so it's 3.05. This resembles more closely the ideal cycle rather than the last one where we had 6 liters per minute. The next one that we have is 3 liters per minute. As you can see, our coefficient of performance went down to 1.72, and the higher the coefficient of performance is, the better it is. So basically, what we're seeing here is that originally we thought the lower the flow rate through the evaporator, the better it was going to be. However, once we got to 3 liters per minute, we could see that maybe it's just a balance. So at this point, you would go in and decide, okay, how high can we get our coefficient of performance without risking costs or things like that? Because as you move forward, you can see that you're just going to have to keep playing with it over and over again to get the best coefficient of performance out of it. This H1 minus H3, that is taken from your refrigeration, and so is your H2 minus H1. There also is another way to get your coefficient of performance where you take the energy used to run the compressor, but that's really not as exact because you don't know if your compressor is constantly running at the same power input. Also, you don't know if there's any sort of loss anywhere else. And that's it.